Hey everyone, today I'm going to talk about starling murmuration and flocking behavior of other animals as well. And I'll begin with a poem from Sparrow Envy by Drew Lanham, a poem called Murmuration. A wave of dark birds surges, a black feathered river rustles, flows on even tide, undulates, tree line to horizon. And what I find so beautiful and interesting about this poem is that the sort of intuitive feel for the birds and their movement is akin to fluid flow and sort of borrows hydrodynamic terms such as a river and undulation to talk about the way that these birds move across the sky. And so we'll start with a little bit of background on flocking and then talk about the physical models that have tried to describe the behaviors that we see. So what we have in starlings and other animals that exhibit collective movement are that there's a self-organization of the constituents, and there's no centralized control, but the group moves coherently, and local rules drive global patterns. And so now let's talk about those models. First, we start with the microscopic models, those that describe the behavior of the individuals in the group. And so Craig Reynolds in 1987 ascribed 3 rules to flocks, or the individuals in flocks, namely that each bird moves in the same direction as its neighbors, remains close to those neighbors, and doesn't collide with those neighbors. And we can see a visual representation in this upper right diagram. And in the model, the way that these rules manifest are that the bird's velocities are aligned, that there's an aggregate, there's a sort of cohesion of this aggregate, and that the birds in the nearest vicinity of each other are repulsed from one another. And then the Vicsek model in 1995 just described a single rule, that the average of direction of the motions is what determines the behavior of each particle in that neighborhood, and related it to the way that a ferromagnet aligns the spins of the particles under the influence, and that there's some strange phenomenon that is aligning the polarization of the flock. And then Toner and Tu come along in 1998 and use hydrodynamic model to talk about the birds, and they take the continuum limit of these microscopic behaviors to look at long time and length scales. And so what they do is they kind of write down these most general continuum equations of motion for velocity and population density that uphold the conservation laws and the symmetries of their problem. And so these are our 3 equations, and just at a first glance, we can tell that there are many similarities to the equations that we've studied in our class, and that there are phenomenological parameters that kind of bury all of the ignorance of the problem, and that there's a conservation of birds. And so this is really interesting, and they find that they can describe and predict what they actually observe in the real world with their model at long time and length scales. Now, another group comes along and says, okay, well, we want to do a better job. We want to understand and replicate behavior on short time and length scales. And they, even find that the turning times of these flocks are occurring on order of half a second, which is really fast and much shorter than diffusion timescales. So information can't dissipate. Another finding is that the birds aren't just following the direction of their nearest neighbors, their 7 nearest neighbors, but they're following the direction sharpness and mimicking that. And that there has to be some sort of spin property that all of the birds have, and that the flock has a conservation of spin, total flock spin. And so each bird is matching the neighbor's spin such that this whole flock maintains that that conserved total spin number. And they also find that if the flock is well aligned, information travels faster, which they posit is maybe an evolutionarily driven phenomenon. And finally, that the same equations that describe superfluid helium are those that they apply to their problem. And so really fascinating to see where the fluid model works and where it breaks. And the sort of takeaway is that on short time and distance scales, the fluid model breaks. And that's where this new model comes in. Thank you.